So in the previous several outings when we were together, we discussed about many things, many aspects, and towards the end we talked about the rotation and the rolling motion, etc. Now today we'll talk about the very fancy concept of gravitation, the gravitational force, which I stated that is the weakest of the four forces known to us and studied by us, gravitation, which has been observed and studied from time immemorable. When we walked, when our forefathers, the children, while walking, they fell down, the ripe fruits, they fell down on the surface, and man in general imitated and learned from other animals also. In the course of that, people knew that there is something like gravitation, that things fall towards the earth and the earth attracts falling things towards it. Naturally, there is an effort when you want to get up and when you want to restrain yourself from falling. The man observed things falling from the sky, that is the rains, the hailstorms and other things. So anyway, there was a notion of gravitation which was present, and then scholars in the bygone era in different civilizations, they contributed to the knowledge about the earthly objects and also the motion of heavenly bodies, the beautiful sky, the very vividly visible in the night, stars twinkling, twinkle twinkle little star, how I wonder what you are, up above the world so high like a diamond in the sky. So there are similes and metaphors and this and that. And the most fascinating thing was, against the backdrop of stars, which almost, and in the case of the several group of stars, etc., they were almost there hanging on the sky. And against the backdrop of the stars, there were heavenly bodies that used to wander on the sky from one place to another place. They were called the wanderers, and today we know as the planets. Initially, man thought that where he is living, he even didn't know that the earth is a round object. Even at that time, they had a model that was put long back by Ptolemy. And Ptolemy's model is known as Geocentric Model, where the earth is taken as the center of the entire universe. And he made as to how the stars are there and they are moving, and particularly about the planets. I thought all the planets are going round the earth. Later on, after much time, there is a mention that Aryabhatta, he rather said that the universe around us is heliocentric. Helio means the sun at the center, and things, they go around the sun. So much so that many hundred years after that, in the backdrop of Europe, there was a monk by the name of Copernicus. And Copernicus, he didn't know about Aryabhatta. Copernicus all by himself, he thought that it is heliocentric rather than the earth was not the center, but the sun was the center. And in the same days, when I say days, it means maybe tens of years, there came up the hero of the modern science, Galileo Galilei. And Galileo Galilei, he put forward many experiments, many arguments in the backdrop of very strict laws that used to exist there, because the church had its own system of science. So in the dialogue of the two sciences and many other works, Galileo did cooperate and rather take the things ahead from the Copernican heliocentric system. Then there comes a wonderful man, a man who could look at the sky and for several years with the naked eye he would fix the movement of the stars and the planets and study all those things and make notes. He was a rich man, and Tycho Brahe looked forward to some help. And there was this young Kepler who helped Tycho Brahe, and he explained the various observations of Tycho Brahe in the form of certain laws. Law of orbits, which he stated that all planets, they move in elliptical orbits. Law of areas, that during the motion equal areas are swept in equal intervals of time. And there was a third law which is known as the law of periods. We will have occasion towards the end of this discussion about the gravitation that I will discuss all these things in a bit detail. So there was Kepler, a beautiful mind at that time, and then followed Isaac Newton. And the story goes that during a quarantine period like these days, Newton was stationed at his mother's place, where an apple fell and Newton had the idea of gravitation. No, that's not true. Okay, Newton was a thinker, philosopher before, and anyway, maybe the apple of Newton, or the apple of what's that company? Apple company. Okay, they have stories, many stories. I can also tell you several stories. You can tell us several stories. So what culminated what came up was the beautiful law of universal gravitation, which was given by Sir Isaac Newton. He was not from the gentry that time, but rather from the working class. What he argued, I am just going to present, and the way he arrived at what is known as the law of universal gravitation. You see, many things were there at that time. Many things were known and people believed in that. For example, the radius of the earth here, which is 6,400 kilometers, as I have told you before. We are not going to use that right now, so I have not written the value. But the time period of the revolution of the moon about the earth, that was studied, and it was believed that the time period of the moon's circular motion, and that in a plane, it's a planar motion about the earth, and that is 27.3 days, which turns out to be equal to 27 into 24 into 60 into 60 seconds. It was also known at that time by several arguments, several calculations, that the distance of the moon from the Earth's center, when both the objects are taken as spherical bodies and all the masses, the mass of the Earth as well as the mass of the moon, they are concentrated at their center of mass. Their composition is taken as homogeneous, and that is, the R turns out to be equal to 3.84 into 10 to the power of 8 meters. Okay? 3.84 into 10 to the power of 8 meters. Now, because it was a circular motion about the earth, that is what he assumed. He did not assume it to be a elliptical orbit. And I tell you, ellipticity, for example, when the earth goes round the sun, or any planet goes round the sun, is a deviation from the circular path. I'll tell you about that when I talk about the Kepler's laws of orbits, laws of areas, and laws of areas is nothing but what we have studied recently, and that is the conservation of angular momentum. Anyway, I am not dealing with that. Now this force is a center seeking force, centripetal force, which we also call a central force. So we can now study the centripetal acceleration. A centripetal is equal to velocity, that is speed of the moon about the earth at a given instant of time, divided by r. And V can be calculated, of course, because we know the circumference of the orbit, because r is known, 2 pi r, divided by the time, which is 27.3 into 24 into 60 into 60 seconds. All those things are there. We have to just substitute the things, and therefore the AC, or the acceleration, turns out to be equal to, like this: 2 pi r divided by t whole square into 1 by r. Okay? Into 1 by r. Because v square upon r gives you this value. And when we substitute these values and make out the calculations, which I am leaving to you, you can verify, this turns out to be equal to, AC turns out to be equal to 2.72 into 10 to the power minus 3 meter per second square. This is the acceleration that the moon has towards, and this is the centripetal acceleration, which is provided by the gravitational force. We see that now the argument is that we see that this value is very small as compared to the value of his ball G, or the gravitational field on the surface of the earth, which can be taken to be about 9.8 meter per second square, and often we take that value to be equal to 10 meters per second square. If we compare that, then there is an orders of magnitude difference between the acceleration, centripetal acceleration, and the value of G. So the value of AC, this acceleration is very small as compared to G. So it was attributed, and it was thought, and Newton saw that yes, there is a beauty in it, and the beauty is that as the value of R is increased, as the value of R increases, so the force and also the acceleration, the centripetal acceleration, they fall with R. The kind of a thing that if R is increased, then A up or F, they will fall. Now, how the fall takes place? Okay. So the force and the acceleration fall with the increase in the value of R. And Newton proposed that F may be proportional to 1 upon R square. F may be proportional to 1 upon R square. And now I want you to recall that I told you when I was introducing you the variables, okay? In the variables I told you that if there is a system where there is a point mass or point charge concentrated at a point here, okay, it is concentrated at the center of a sphere, at the center of a sphere. And remember, my way of thinking is that because something goes out of this point, which can be a mass, which can be a charge, but this is a point object, and the effect as the radius keeps on increasing, now it is less. If the radius goes on increasing, then you can say that the effect becomes smaller and smaller as this thing increases. And you know that the surface area of a sphere is 4 pi r square. So the effect will be equal to something. I wrote there that there is something which is fluxed out or fluxed in, okay, going out of this through these spheres, something divided by 4 pi r square. This is not the argument that was given by Newton, but I, having been impressed by Gauss, I myself evolved this thing that for a secular system like this, remember, I use the term secular. Secular means no preferred directions. The effect, it spreads in all directions without any preference. So what is there? There is something. That something could go out, and that something could also be concentrating over here from outside this sphere, coming over here and focusing out over here. In both the cases, if the system is secular, okay, then the effect is proportional to that something divided by 4 pi r square. And so you can see that the something is a constant, 4 is a constant, pi is a constant, and therefore my effect is going to be proportional to 1 upon r square. But Newton came out with a conjecture that this could be proportional to 1 upon r square, which we discuss shortly. So we obtained from the experimental data for the Earth and Moon system that we found that the acceleration, centripetal acceleration of the Moon towards the Earth, it turned out to be 2.72 into 10 to the power of -3 meter per second square. And the value of g that was calculated at that time, and it was calculated much before by Galileo, that is, in the surface of the Earth is taken as approximately equal to 9.8 meter per second square, often it's 10 meter per second square to ease the calculations. Now, Newton made the proposal that the ratio of the two shows that as we go away and away and away from the center of the Earth, so the value of the AC keeps on decreasing, decreasing and decreasing, and so the force will also keep on decreasing and decreasing. So he made a beautiful proposal, the genius that he was, and he thought that the gravitational force or AC is proportional to 1 over r square. This law, this is used often. For example, I told you that in case of the Coulomb's law for a point charge, this is again there 1 upon r square. Also, this is the same kind of inverse square law is used in luminance problems associated with light. So, if this is so, if we believe that the gravitational force or the AC is proportional to 1 over r square, so then G becomes proportional to 1 upon RE square, where RE is the radius of the Earth, because we are talking about the surface. And considering the Earth to be a point mass concentrated at its center, and the body under consideration of the surface of the Earth having another mass, so the G is proportional to 1 over RE square, because the two things should be similar. Now look at what he did. He was a genius, no doubt about it. So he divided AC by G, left hand side, by left hand side, and right hand side by right hand side. So it turns out to be equal to 1 upon r square divided by 1 upon RE square. So this becomes equal to RE square upon R square. Okay. RE square upon R square. Now, at that time, there was another result that was well established, and it was believed by all and sundry at that time, and Newton also believed. So he found that the ratio of the radius of the Earth and the radius of the sun's moon's orbit around Earth This is equal to 1 upon 60. Okay, is equal to 1 upon 60. So if so, then by this relation we can calculate that AC will be equal to G into RE square upon R square, which is 1 upon 60 square. So this AC turns out to be equal to 9.8 into 1 upon 60 square, that is 3600. And when we make the calculation again, then what we find is that the value turns out to be equal to 2.72 into 10 to the power of minus 3 meter per second square, which is in correspondence with this value. The earlier value and the value that has been determined with the help of considering the gravitational force to be proportional to 1 over R square. So that means now the theory and the experiment, they are in agreement. One result conforms to the other result. So that is why we have to give in that the gravitational force is proportional to 1 upon R square, and there is a confirmation of theory with the experiment, which is one of the best ways of doing physics. And then Newton proposed that if there are two masses, m1 and m2, held a distance r apart, okay, then if they are held like this, I don't know how come, then what happens is that there is a force of attraction here also and here also, F12 and F21, etc., etc., which is confirmed by the Newton's third law of motion. The magnitude, both the magnitudes will be equal, the direction will be opposite, and it will be a attractive force. So what he found is that if we keep the value of m2 constant, the value of r constant, and only change the value of m1, so what will happen is that there will be direct proportionality between f and m1. And similarly, if m2 is changed but m1 and r, they are kept constant, this I have discussed earlier also, then f is proportional to m2. And the third law which we confirm is that if m1 and m2, they are not changed, only the distance between the two is changed, then this will be, I'm sorry, I could write this as, instead of this, I could write this as small r square, small r square here. So f is proportional to m1, f is proportional to m2, and f is proportional to 1 over r square independently. So we find that if all the three values are varied at a time, then f is proportional to m1 m2 upon r square. So again, small r square as I have taken for the case of these two non-celestial bodies, then it turns out to be equal to capital G m1 m2 upon r square. Allow me to change this again to small r square. Okay. So this is the formula that we obtain for the force of attraction between these two bodies. Of course, their sizes are considered to be small. They are considered to be point masses almost, okay, not in extended bodies. Now, what is interesting is that this capital G, it does not depend upon the mass or size or composition of the first body or that of the second body. and also it does not depend upon the value of r, and therefore that is why we call capital G as the universal constant, a constant which does not depend upon the location, upon the composition, upon the shape and size of bodies and the separation between the two bodies. It is always true. That is why we call this capital G as the gravitational constant, which is universal in nature. When you work out the values, capital G is equal to 6.67 into 10 to the power of 11 Newton meter square upon kilogram square. And here I have just tried to give you the dimensional analysis. This is force, MLT minus 2, this we should remember by rote, and L square upon M square. So this turns out to be equal to M power minus 1 L cube T minus 2, and that is the dimensions of this quantity. But the unit is obtained retaining the value of the force, unit of the force, Newton meter square per kilogram square. Now, to wind up, I would like to present the same law in vector connotation. In vector notation, I have vector F is equal to, the same values are there, G M1 M2 upon R square, okay, but now what we have is R cap and a negative sign over here. So R is, it can be equivalently written as minus capital G M1 M2 upon R cube into the vector R. Okay, the minus sign shows that the force is attractive in nature. In general, if the force is attractive, then there is negative sign. If there is a force, as in the case of the Coulomb's law that we discussed earlier, it could be possibly repulsive also. In the repulsive case, the sign over here will be positive. So what we have done is, we have just discussed gravitation, and we have discussed how the story of from time immemorial to the days of Newton to the present day, I established everything, and then the beautiful mind of the man who is Newton, the man who was in quarantine at the time of the great London plague. Newton beautifully thought, and he assimilated the law, which is equally applied to the case of celestial bodies as to the case of earthly bodies. And the beauty of the proposal was that this is gravitational force, or the central acceleration towards the centripetal acceleration towards the center of the Earth Moon system, the gravitational force is proportional to 1 upon R square. The same result was extended, the same thing, same argument was extended in understanding what happens at the surface of the Earth, solely because of the Earth itself. And then we found that since it was known by calculations in those days that the ratio of the radius of the Earth to the radius of the orbit around the Earth, that of the Moon, it was equal to 1 upon 60. Very interesting result. And then we calculated the value of AC, putting the things in this equation, and we obtained that the value of AC is again 2.72, in close vicinity of the value that we had over here. So it shows that the theory and experiment In this theory, the theory is that AC is proportional to 1 upon r square. Okay, I prove to you exclusively in the case of a spherical body with a mass, a charge at the center of the body, which I call something which is coming out of it or something which is going into it. So per unit area, the effect was that something divided by 4 pi r square. We did show that in secular systems, what I call a secular system means there is no preferential direction. When there is no preferential direction, then this kind of a relationship does exist. But Newton was a genius. Newton, he found his ways to show that yes, the inverse is square law will hold. And when it does, of course I would like to make a comment. In some books I found that they write that F is proportional to the product M1, M2. M1, M2. I don't subscribe to that. It's instead F is proportional to M1 and independently proportional to M2, and therefore according to the mathematical techniques tools, I can write that F is proportional to M1, M2 upon R square. Okay. Anyway, if you want to subscribe to what the books say, that F is proportional to M1, M2, F is proportional to 1 upon R square, and thereafter you get this kind of a relation, well and good. I don't insist. I don't look down upon anyone. They have their own ways of presenting the things, but in my opinion, humble opinion, I'm a very humble person, I'll say that F is proportional to M1, F is proportional to M2, and F is proportional to 1 upon R square. And similarly in the case of the Coulomb's law, also I said to you before, in a multivariable system, that F is proportional to Q1, is proportional to Q2, is proportional to 1 upon R square, and similar kinds of things happen. In fact, what we'll see in the lectures to come, that similar kind of mathematics, similar kind of arguments we give in both the cases of the Coulomb's law and this law of gravitation, and also in the case of when we discuss illumination of point sources of light, there also we have the same kind of a mathematical build-up that we make. So I have enjoyed today, and I understand that you must also have enjoyed. Okay, no need to say every time UQVA, okay, but I will welcome your comments, your questions, etc. in the comment section of my video. Thank you very much. So kind of.